In the last lesson, we looked at a few exponent laws. We looked at the law for multiplying powers together, the law for dividing powers, and the law for raising one power to another exponent. Here's a couple more rules that you need to know about exponents, which once you memorize the rules will make your life easier. If you don't memorize them, then it's going to seem like a mystery. So you do have to put a little bit of effort into memorizing them. The first one is really easy. Zero exponents. Anything raised to the exponent 0 is equal to 1, as in the number 1. 2 to the exponent 0 equals 1. If you have a calculator handy, and you should, try 2 to the exponent 0 and you'll see that it equals 1. So it is 3 to the 0, or 4 to the 0, or 10 to the 0, or 100 to the 0, anything to the 0. This one is 1,000,000 to the 0. That's still going to equal 1. Check it out on your calculator. In fact, I'll check it out on my calculator. So I've got one right here. Alright, let's see. 1,000,000 to the exponent 0 equals 1. Beautiful. (13 to the 0, 1. 25 to the 0, 1. Negative 1 to the exponent 0, also 1. Interesting. So negative numbers inside brackets still equal 1. So these brackets, remember this 0 is on the whole bracket. But if we compare that, say I had negative 1 like this without brackets to the 0, well, now that negative 1 is the only thing that the 0 is on, and so that 1 is the only thing that's on. The negative stays out front, and so in this case it would be negative 1. So again, the rule is consistent, but the brackets make a difference. Negative 5 to the exponent 0, 1. Alright, so that's an easy rule, as long as you're careful paying attention to when there's brackets. Now, negative exponents, they're a little bit harder. Anything raised to a negative exponent is equal to 1 over the same base raised to the same positive exponent. So, what that means, so we'll do 1 over the same base raised, and we'll just drop the negative sign. Let's put it that way. So there's two parts. 1 over, so that's where let's actually highlight two different things. So here's the 1 over part. Here's the 1 over part. Then the same base raised to the same positive exponent. So those are the two different parts. And 2 to the 1 is just 2. So 2 to the negative 1 is the same as a half. Alright, then we have 1 over 2 to the same exponent but positive. So again, there's the 1 over part. Here's the same exponent but positive now. It's positive 2. And we know that 2 to the 2 is 4. So 2 to the negative 2 becomes 1/4. This becomes 1 over 2 to the positive 3. And 2 to the positive 3 is 8. Let's try some different bases. Now it's 4. So it's 1 over 4 squared. So we're still doing the same thing. It's always 1 over. And we're always keeping the same base, whatever we started with. Then you just have to figure out what the bottom works out to. Sometimes you have to do that. So 4 squared is 16. This would be 1 over 5 squared, which is 1 over 25. This would be 1 over 695 to the 1. But if it's just 1, then I know it's just I don't need to write that exponent down. So it's just 1 over 695. Fractions are a bit different. So I could still apply the same rule as above. The problem is I'd end up with fractions within fractions. I'd end up with 1 over 1/5 squared, which I can do, but then I'd have to solve that and work it out, and it's really ugly to have fractions inside fractions. So instead, I'm going to show you a better shortcut for fractions. So instead of doing 1 over for fractions, what we want to do, I'm going to write it as a rule, for fractions, flip and make the exponent positive. Flip what? Maybe I should have put the word flip the base in here. Flip the base, the fraction base, and make the exponent positive. So again, there's two things happening. So instead of doing 1 over, like I could do, but it's awkward, I will flip the base. So instead of 1 over 5, I get 5 over 1, and then I'll make the exponent positive. And then I can carry on from there. We know that 5 over 1 just equals 5. So that's the same as 5 squared. And then I have 25. So flip the base for this one. I get 3 over 1 to the positive 4. There's the flip the base part. There's the make the exponent positive part. 3 over 1 is just 3. 3 to the exponent 4 means 3 times itself 4 times, which equals 81. Now, let's add one more example, because sometimes we won't have a 1 on the bottom. Both of these had 1 on the top. What happens if I have something else on the top? Say I have 2/3 to the negative 3. Okay, well, we can still flip the base. Now I've got 3 over 2 to the positive 3. But then this means the same thing as 3 halves times 3 halves times 3 halves, right? Here's another way of looking at it, though. Again, this is just sort of a shortcut or simpler way of doing it. Think of putting this, if I want to get rid of the brackets, which I eventually do if I want to simplify this, think of putting this 3 exponent on both the top and the bottom. And so then I've got 3 to the 3 over 2 to the 3. And then 3 to the 3 is 27, 2 to the 3 is 8. That would be my final answer. So we want to do a bit different for fractions. Not hard, you just have to know the tricks. So here's a couple of examples. Write each expression as a power with a negative exponent. Well, in all the examples I've done so far, I was taking them from negative exponents and giving them positive exponents. So this is just going backwards from what I just did. So going backwards, I could think 7 to the negative 11, and I could, sorry, I'm just pausing because I want to think of the clearest way to explain it. Ignore what was written there originally. Look at the 7 to the negative 11 that I just wrote down. Now imagine it was going back to the top of this column where I had, say, 2 to the negative 1. Let's look at 2 to the negative 1. So the rule was write 1 over the 2 and then drop the negative exponent, so it was 1 over 2 to the positive 1, which is a half. All I'm doing is doing an imaginary thing where I'm sort of going backwards and saying, well, what would I have to start with to get this fraction 1 over positive 7 to the positive 11? Well, if I started with 7 to the negative 11, then I would do 1 over 7 and then just drop that negative sign, which takes me back to this. So there's a roundabout way of explaining it, but I can't think of a clearer way of saying it. It's asking us to go backwards. So 1 over 7 to the 11 is the same as 7 to the negative 11. What would I have had to start with for B part to get 1 over 3 to the 20? Well, going backwards, the base was 3, and the exponent was 20. I must have just started with 3 to the negative 20. Write each power as an expression with a positive exponent. Well, that's what we've already done in our table up above. 1 over 5 to the 2. And in fact, that's all they ask us to do. They don't ask me to expand it out. They just want to leave it with a positive exponent. So that would be the end of that one. This would be 1 over 3 to the positive 4. Example 3, evaluate. Okay, so now this one is asking me to first change it like in example 2, but then to keep going with it. So the first step of changing it, it's 1 over 2 to the positive 4, but then I know that 2 to the positive 4 is 16. 2 times 2 times 2 times 2 is 16. Or you could put that in your calculator. This would be 1 over negative 2, still with the brackets on it, to the positive 3. All right, that's fine. 1 over. Now, negative 2 to the positive 3, we already talked about in a previous lesson, odd versus even exponents on negative bases. So this is an odd exponent on a negative base. When I multiply negative 2 times itself 3 times, it's still going to end up being negative, and it's going to be an 8. So in other words, so it's going to be 1 over negative 8. But the reason why is because of that negative 2 to the 3 means negative 2 times negative 2 times negative 2. And negative 2 times negative 2 is positive 4. And positive 4 times negative 2 is negative 8. So because it was an odd exponent, 3, 3, 5, 7, 9, 1, then it's going to stay negative. If it had been an even exponent, then as you can see, negative 2 times negative 2 was positive 4 when I explained it. So it's going to be, that would turn out being positive. As we're going to see actually in this next one. 1 over negative 2 to the positive 2. Well, that means 1 over negative 2 times negative 2 is positive 4. Then we have a fraction 1, so we're going to flip it upside down. 2 over 1 to the positive 3, and 2 over 1 is just 2. 2 to the 3 is 8, and that's it for that one. Write each expression as a single power, then evaluate. All right? Well, now we're going back to what we learned in the previous lesson. We are multiplying powers with the same base, so we're going to add the exponents. Negative 4 plus 7 equals positive 3. Then evaluate. All right. 2 to the 3 equals 8, so that's the second part. And then evaluate part. Again, we're multiplying, so we're going to add the exponents. So we've got 1/2 is our base. Negative 3 plus 2 is still negative 1. So there's my first part where I've written as a single exponent. But now I have to evaluate it. So for our fractions, remember what we did is we flipped the fraction, dropped the negative sign. Anything to the exponent 1 is 1. Sorry, not 1. Anything to the exponent 1 is itself. And what's inside the bracket simplifies just down to 2, so that would be the answer there. 2 over 1 is just 2. In this case, we're dividing for C part. So this would be, now this one's a bit tricky. Let me actually write out what's going on. We know that we have to subtract the exponents, right? But, so we got 2 minus, but we already have a minus sign written in here. So we're going to do 2 minus negative 2. There's 2 negatives. We got the minus, which comes from the dividing, but we also have the minus that comes from the negative 2. So that's the same as 2 plus 2, which equals 4. And then to evaluate it, we get 3 to the exponent 4 equals 81. And then we have powers of powers. We know in this case we're going to multiply the exponents together. Negative 2 times positive 2 equals negative 4. So there's as a single exponent, single power. Now we'll go 1 over 5 to the positive 4. 5 to the positive 4 equals 625. And so that would be the answer for this one. And last example. Use each indicated base to write each numerator and denominator as a power, then simplify. Express your answer as a power with a whole number base. All right, bit of a confusing one, so let me walk you through it. They want me to, first of all, rewrite 81 and 27 as powers that have a base 3, so they're equal to each other. So in other words, what exponent do I need to put on 3 so that it equals 81, or 27 in that case? So I need to have it as 3 and 3. I need to put exponents here, though. So I need to have an exponent on this and an exponent on this so that they're still equal to what's right above it. Well, 3 to the 1 is 3. 3 squared is 9. 3 to the exponent 3 equals 27. So that means my exponent here in the bottom has to be 3. 3 times 3 times 3 gives me the 27 on the bottom. If I multiply times 3 one more time, I get 81. And that's what gives me, 3 to the exponent 4, in other words, is equal to 81. And you can confirm both of those things on your calculator. 3 to the 4 is equal to 81. 3 to the 3 does equal 27. So they wanted us to rewrite it first with common bases. They have the same base. And what's good about having them both be base 3 is now we can use our exponent laws to simplify it. We know that we can subtract the 3 from the 4 because we're dividing, and we just get 3 to the 1 or just 3. So that's what this question wants. For this one, we want a base of 2. So in other words, we're going to rewrite 128 as 2 to the something. We're going to rewrite 16 as 2 to the something. Let's start with 16. That's an easier one. 2 squared is 4. 2 cubed is 8. 2 to the 4 equals 16. If I keep going, exponent 5 would give me 32. 6 would give me 64. 7 would give me 128. I'm doubling it each time as I add 1 to the exponent. So that's the first part. Now again, using our powers, division of powers rule, we're going to subtract the 4 from the 7, and we get 2 to the 3. And then we know that 2 to the 3 is equal to 8. So we did this whole thing without any need of a calculator if we understand how the exponents are working.